In this video, we investigate what's called improper integrals. Let's recall the integral or definite integral we introduced before. Definition of a definite integral is a limit of a sum called Riemann sum. For example, if we have the graph of f of x, it's a quick review shown here. Now, to estimate the area of this shaded region, what we do is to divide this region into n parts, slice it up into n sections. Pick up a section or strip. The thickness is called delta x I, and we regard this approximately as a rectangle. So the height is the value of function at some point x of I, some point taken from this subinterval delta xi. So approximately area of the strip is same as area of this red rectangle, which is the height times the width. So product is area of this strip approximately. Then we add all those areas of strips up and send the n to infinity. What that means is we really would divide this into infinite many strips and check out the limit. The result is denoted using an integral expression. So this is how we introduce the definite integral. Now, let's consider an integral, say 2 to infinity 1 over x squared dx. We would go through similar process. For example, we can think of this as integral that represents area of a region, say from 2 to infinity. Now, if we try to do similar thing, like divide this up into n parts to start out, we have problem right away, because if we try to do this, now how we slice it up, the process, if you check out up here, is we divide this first of all into n parts, then send n number of strips to infinity, check limit. Now the total length of this interval is infinity. So if we divide this interval into n parts, one part at least would have infinite length, means one of those guys is going to be infinity. What does it mean? You know, some height times infinity. We can even take this very, very, very small, but still it's not clear what kind of product this is going to be. Very small number, or it's just, it would be actually infinity if no matter how small this is. If this guy is infinity, one product like this would be infinity already. So we cannot do the problem the way we would with a finite interval a to b. So the problem is the upper limit in such interval is infinite. This makes this integral improper. Does it mean there's no way to do it? Not necessarily. We just have to find a way to somehow take care of, the trouble, potential trouble caused by this infinite limit, upper limit. So this is one kind of improper integral. Now let's check out another integral. Well, if you graph, actually, so this is y-axis. Suppose this is a 3. If you graph this function, it will look like this. So this integral would represent area 2 to 3. Now x equal to 3 will be a vertical asymptote for this graph of 1 over x minus 3 squared. So again, if we take the normal approach, that we would try to slice this into, say, n parts and send them to infinity. See what will happen. Okay, we start with the n parts. This time we check this, for example, loss strip. Now the width delta x can be very, very small, but as we increase the number of strips, this strip gets narrower and narrower, which means the usual way to construct rectangle would require the height to be, well, very, very, very large, because this graph goes up vertically, pretty much approaching this line. So the closer, the point is to 3, the larger the value. There's no limit, because really it's like a undefined, it's infinity. So in this Riemann sum, the last product f of x sub say n delta x of n is undefined, because it's not clear what we're going to get, because this will approach infinity. This value will approach infinity. At the same time, the width will approach 0. So even this one term alone is not clear as what it's going to be. So this integral, well, in normal sense, is undefined, cannot be treated in the old-fashioned way. In other words, this is another type of improper integral. So, well, from these two examples, we've seen the two different types of improper integrals. One is clearly if the limit is infinite, upper limit or maybe lower limit. Improper, we just cannot do it in the old way. Or like this integral, the limit seems to be fine, 2, 3, trouble is function is undefined at 3 upper limit. Maybe the function is undefined at the lower limit. Function can be even undefined at the number between 2 and 3, which we'll examine later on. So if any of these things is true, it's just not possible to come up with even one product, in the Riemann sum. So we just cannot do it this way. So now the question is, then how are we going to try to come up with a way or some idea to calculate area of a region like this, or area of a region like this? Well, let's examine this integral again to get some inspiration. Well, I'm going to start with that. So what we do is, well, the problem is the same thing. So we'll try to calculate area under the graph from 2 to infinity. Now graphically we can do this. Practically we cannot go from 2 to infinity right away. We can go from 2 to some point called B, say very, very far from 2. Now it's a finite number, unspecified. Well, we can definitely do this area, because this would be a normal area problem, normal integration problem. So we would try to figure out just the area of this green shaded region. As you can see from the graph, if we, once this is done, so we get the area, of course it would involve B, it would be a function of B basically. Now once we find the area of this green shaded region, we push B towards infinity. Mathematically, this can be done through this limit process. So it will make sense as we push the B further and further away from 2, closer and closer to infinity, taking the limit. So imagine we would be approaching area of the whole region that we wanted to do. So this would be a sensible way to try to evaluate this kind of improper integral. Mathematically, we can prove it. Graphically, it makes sense to do so. So that's how we come up with this idea, by examining the situation graphically, get the idea. So in general, if we have an integral, improper integral, involving infinite limit, we go from A to some B, with the intention to send B to infinity, as shown in the graph. Once the integration is done, we send B to infinity. Now, well, this is the definition or formula. With a specific improper integral like this, what I do actually is I don't need to memorize the formula. What I do is this: I just draw number 9, always a number 9. Say I want to go from a to infinity, which of course practically is not possible. Inspired by the graph, by the definition, I say, well, okay, I cannot go from a to infinity, I can go from a to b. Because the b will be sent to infinity, so I place b much closer to infinity than the other end. This way, the number 9 guides me to come up with the correct expression. So I'll integrate from a to b, and then b will be pushed to infinity. So come up with the correct limit expression. It is very important to do a number 9 like that. Without number 9, people often get confused as how to set up the limit. B approaching infinity, positive infinity, or negative infinity, or number can be pretty confusing. Alright, let's see one example. Here's an integral from 5 to infinity of 1 over x minus 1 quantity raised to 3/2 power. So number 9. Original problem, we're supposed to go from 5 to infinity. Now, infinity, of course, is the thing that causes trouble, making this improper. So I'll avoid this infinity. I say I'm not going to go all the way to infinity. I'll go from 5 to b first. So again, this number 9 shows me how to set up the integral. So I'm integrating from 5 to b first. Once this is done, I'll send the b to infinity, positive infinity here. Well, the rest is to evaluate this expression by work on the definite integral here. The definite integral here is a normal integral from 5 to b. Both are finite. 5 is a finite number, b is a finite number too. It's unspecified, so we know it's finite. So let's work out the integral first on the side. 5 to b. Integration is just like before. Do a substitution. U equal to x minus 1, du equal to dx. So this is 1 over u to 3/2 power. Dx is du. The antiderivative, let's see, negative 3 over 2 du. One over negative 3 over 2 plus 1 u raised to negative 1/2, or negative 1/2 or negative 2. U is x minus 1 half power put on the bottom, so it's 2 over x minus 1. half power is the square root. Now I got x back. I'm going to put it v in, 5 in. So this expression becomes negative 2 over b minus 1 half power plus 2 over 4, 5 minus 1. This actually is 1. Let's simplify. Why not? 4 half power is 2, so it's 1. So this is the value of this definite interval in the limit expression. Let's plug in. So this is 1 minus 2 over b minus 1. So we're done the first part. Definitely interval involved. The finished up, send b to infinity. So let's look at the number 9. Actually, this expression inside parentheses would represent like an area under the graph from 5 to b only. Now if we push b to infinity, then the answer would represent area under the graph from 5 to infinity. So let's see what it is. So b goes to infinity, okay, b is infinity here. Infinity minus 1 is infinity. Infinity raised to positive power is infinity. 2 over infinity is 0, so it's 1 minus 0. Answer is 1. So 1 is the value of this improper integral. Now, for any type of improper integral, we have to do all this work. In the book, for improper integral, we are supposed to actually determine whether the improper integral converges or diverges. What it means is, well, based on the value of the limit, if the value is finite, like this, we say the improper integral converges. Otherwise, we say the improper integral diverges. Now, so there are actually 3 possibilities when you do the limit. When you do the limit, the answer could be a finite number, so converges. You claim the improper integral converges. That's the answer they want. Of course, you have to do all the work no matter what. Different problem if the limit becomes infinity, which is likely because this thing goes to infinity. If the answer is infinity, you say diverges. If it's impossible, it's not impossible. If the limit does not exist, undefined, you also say diverges. Suppose you end up with the sign b somehow in one problem. B goes to infinity. Well, you cannot do limit because when b approaches infinity, sign will just go up and down like this. It's impossible to find the limit. The limit doesn't exist. So this kind of situation or this kind of situation, we would say the improper integral diverges. Alright? So let's record here again for improper integral involving infinite limit. Say from a to infinity, we go from a to b first and send b to infinity. This basically allows us to avoid integrating with the infinite limit involved. So the infinite limit is the trouble factor. We avoid it first. Just go a to b with a number now. A to b. Once we're done that, we send b to infinity. as shown through this example. 5 to infinity to a number 9, stop at B to avoid infinity or infinite limit. 5 to B, B goes to infinity. So do the integration, get the answer. Of course I did on the side, and find the limit. The limit is finite number, integral converges. If the limit was infinite or undefined, we would say the improper integral diverges. Now let's examine the other kind of improper integral. Again, we use this integral to get some expression. We had this before. The graph looks like this. This is a 3. Say this is 2. We wanted to find the area here. Investigate the area here. How we do it is, well, in this problem, 3 is causing trouble. It's a finite number. It's causing trouble because the function becomes infinity, undefined. So the same strategy, we would go from 2 to some number here called B. It's perfectly normal to integrate from 2 to B. That would give us the area here. 2 to B, not up to 3. We're avoiding 3 in the beginning. Once we find that, we send B to 3. We take a limit. Actually, B is always on the left side, so it's a left side limit. So this would give us the value of this improper integral. Of course, like the other type of improper integral, depending on the outcome. If the limit is a finite number, that converges. If the limit is infinity or undefined, we would claim that the improper integral diverges. The same way we draw conclusion. Just now it's a different type of improper integral. There's no infinite limit involved. It's the function that's undefined somewhere. So from this, then we come with our formula or definition. Suppose we have a to b, assuming f of b is undefined, infinity. So what we do is, again, through number 9, a to b, b is trouble, so we don't go all the way to b. We go from a to some capital B, and this is no trouble because it's assumed that f is only undefined at right endpoint B. So from a to capital B, no matter how close the capital B is to that, it's fine everywhere. Once this is done, we send B, capital B, toward B minus. Now similarly, you can imagine if we have a to b f of x dx. Well, fa is undefined, so that's trouble spot. What happens is this time we would still start with the number 9, a to b, Now this time this is a trouble spot, so we avoid it, pick up some location called capital A. Then we do capital A to be f of x dx. This is perfectly fine, normal, definite interval. Once it's done, keep in mind this time we intend to send a capital A towards the little a, so we just do a limit a to a plus, because a approaches little a from the right hand side, so we just do a right hand side. So from this or this or before, you can see our strategy is to try to avoid the trouble spot first, whether it's an infinite limit or point where functions are undefined. Alright, let's see one example. Here I have a integral 1 to 4 square root of x minus 1. Now it's clear. The function is undefined at 1. So let's start with the number line. 1 to 4. Function is undefined here. So we're not going to go from 1 to 4. We go from some location called A, very close to A at 1. So mark this location close to 1 to remind us that eventually B, this A, will approach 1. This A will approach 1. And then number 9 here shows us how to set up the correct integral, the correct limit. Okay, so we're going to start with A to 4. Once this is done, the A will approach 1 from the right hand side. Just like the first example, then we'll just work out this first and do a limit. Let's see, A to 4 square root of x minus 1 dx. I'm going to do substitution, u equal to x minus 1, du equal to dx. So this becomes 1 over square root u du, or negative half power du. Simple integral. This is positive 1/2. Flip it, so it's 2. U is x minus 1. 4 A. Now plug in. So the main work, we figure out the integral capital A to 4, which is 2 times that's like 3, so square root of 3, that's a final number there, minus 2 times square root of a minus 1. Alright, now send A to 1. A approaches 1 from the right hand side. A is always more than 1, but as the value of A gets closer and closer to 1, we see this thing approaches 0. So this limit is 2 square root 3, 2 times square root 3. The answer is a final number again, so we claim this improper integral converges. Now finally, let's see an example where the trouble spot is not at the endpoint, not infinity either. So let's see. We want to check out 0 to 2, x squared minus 1 on the bottom, x on top. There's nothing wrong at 0. The function is defined as 0, function defined as 2. You can see the function actually is not defined at 1. So 1 is a trouble spot. That is in the middle. What do we do? Well, let's start with the number line first. So 0 to 2, and we find out 1 is a trouble spot. So this kind of problem, we split. We split this into two integrals, 0 to 1, (1 to 2). This way, we have an improper integral with the upper limit as a trouble spot, another improper integral with the lower limit as a trouble spot. And we just deal with each separately. The first one, let's see. So 0 to 1. Now 1 is a trouble spot, so we go from 0 to b. Alright, so let's do the separately. 0 to 1, x squared minus 1 dx. We will go from 0 to b first. Send the b to 1 from the left side. Well, just like the previous example, we're going to evaluate the integral first and do the limit just for this guy. Okay, do the integration. Integration is pretty simple. I'm going to just get the answer with a simple substitution. U equal to x squared minus 1. It's going to be 1/2 log x squared minus 1. With the b and 0 plug in. So b plug in is 1/2 log b squared minus 1. The half 0 plug in is 1. That's 0, so it becomes 1/2 log b squared minus 1. Actually, we know b is less than 1, so we can actually get rid of the absolute value. It's 1 minus b squared. So integral is 1/2 log 1 minus b squared. Now, when b approaches 1, so this approaches 0. When this approaches 0, it's infinity. It's a negative infinity, actually. Well, the second one, we would similarly set it up. Let's see. So for the second one, it would be 1 to 2 we wanted to do. X squared minus 1 dx. We would do a number line again. For the number line 1 to 2, the trouble spot is 1, so we would start from sum A. Just to set it up, it would be A to 2. When this is all done, we would send A to 1 from the right hand side as shown from the number line. Alright, now because the work will be similar to this, just doing do integral and do a limit. Now, actually, because the green guy diverges, we don't really even need to worry about what would happen to this. So for improper integral, which is split into two or more, if one part diverges, the whole thing diverges. You don't have to worry about that. Alright? So our conclusion: this integral diverges. Now, I just want to show you when something is wrong, between the endpoint, like a 1. What happens is you just split it into 2. Now, if it's improper integral involving both infinite limits, assuming nothing else is wrong, if functions are defined as somewhere, that's just more complicated. We're not going to talk about that. Just say infinite limits. Those are the factors that make this integral improper. So similarly, what we do is this: infinity to infinity, negative infinity to infinity. And we just split, just pick up some value in between. You can pick up 0, you can pick up -1 or +5. Say +5. Just like the previous example, we would split this into negative infinity to 5 as 1, and 5 to positive infinity as another. We check out. Same is true if one of this split improper integral diverges, the whole thing diverges. So for this thing to converge, each every one would have to converge. The each every one would be like how we did it. Showing the first example like this. With infinity, just avoid that first and set up. This is the complete example. Just avoid infinity. You don't go from 5 to infinity right away. Go from 5 to b, and then send b to infinity. Alright, so this is how we evaluate improper integral.